I'm working through the problems from chapter 2 of this book, Problem Solving Strategies by Arthur Engel. And there are 38 problems in the chapter, and I've got up to 15, so I'm hoping I'll manage to do at least 4 problems in this session, so then I'll be halfway through. Not that it matters too much. These problems come from a chapter called Colouring Problems, I think is what it's called. They're colouring proofs, and the idea is that you're given a question and to answer it, usually you need to come up with a colouring. Actually, 1 or 2 of the questions have been questions about colourings, but usually the technique is you come up with a clever colouring that shows that something is impossible. So I'm going to move quickly to the first question that I haven't yet done. So that's question number 16. On one square of a 5x5 chessboard, we write -1, and on the other 24 squares we write +1. In one move, you may reverse the signs of one A by A subsquare with a greater than 1. My goal, it's an interesting use of pronouns here, so you may do such and such, but my goal is to reach +1 on every square. On which squares should -1 be to reach the goal? Okay, so that's quite interesting. I noticed that, so this is question 16, I noticed that we can express that if we want to as a linear algebra question over F2, by which I mean we have a 5x5. We can think of each potential, maybe instead of 1 and -1, I could have noughts and ones. So 0 corresponds to 1 and 1 corresponds to -1. So I have a sort of 5x5 grid filled with noughts and ones, and at any stage I can take some kind of square inside and add the all ones vector in that square, and I want to know if I start with a 1 in one place and noughts everywhere else, can I end up with noughts everywhere, which is another an equivalent way of saying that is the vector that has a 1 in that one place and noughts everywhere else generated by these characteristic functions of squares, mod 2. So let's just see what we can do, if anything. So for example, if I take a square like that, I'm not going to say actually how big it is, but I just want to try to generate something interesting out of it. So if I then maybe take another square like that and another one like that, right, if I add those two together, I'll just get this L shape here and this L shape here. I've had them together mod 2. If I add the entire square, then I end up with this, this, and this. And then if I add that square and that square, I get to this one. So let me just, I've actually just shown that we can get the corner squares, so I'll just be a bit more explicit about how to get a corner square. So what I do is, I'll draw a slightly nicer picture than I had before. So I'll flip everything in the entire square. So I'm going to sort of put a sort of dark boundary for each square that I've actually done this to. And then I'm going to do just a moment. Something I think I thought maybe I haven't done what I thought I had done. So what happens if I do 4, then I'm left with a 1 over there, but I'm not allowed 1 by 1 squares. So let's try a 3. But that, if I now have another 3 here, that's not quite going to do what I wanted, because now I've got this and I've got this. So it was just count. Everything's in the. I'm trying to generate just the top left-hand corner. So I need to find a bunch of squares such that the top left-hand corner is in an odd number of them, and everything else is in an even number. And so far, those things are in an even number. Those things are in an even number. That's in an odd number. But all this region here is in an odd number, and that region here is in an odd number. So can I make this funny region here? Well, I can, not so easily. I can sort of get rid of those by putting in a 2 by 2 square. That'll make that even, but then I've got this 3 by 1 and this 3 by 1 here. So something I made a slip somehow. Can I use this argument, however? I think I can use this argument to get the center square, so let me just, I'll draw it more quickly. So if I put a 3 by 3 and another 3 by 3, I think if I do 4 of these, I'm going to be in, no, wait a minute. So that one I've now covered twice. That I've covered once, that I've covered once. This I haven't yet covered, but if I put in this square here, this 2 by 2, and this 2 by 2, then I've covered that, and that once. This one twice. So that's even, and everything else is odd. So if I now do the entire square, then that flips it round, and that makes this odd and everything else even. So center square is fine. I'm beginning to think the corners may turn out to be impossible. What about something just a little bit off center? Is that going to be problematic in some way? It seems to be difficult to achieve this, what I've done here. So I think it's time to start thinking about colorings, having established that it can sometimes be done. And so I want to think about what might happen, so to speak, evenly. Whatever square you put down that has size more than just one. Oh, just a moment though. Supposing I have a 3 by 3. Oh no, that doesn't work. I was going to say maybe the same argument works, but then these two corresponding things will be 1 by 1s. So let's forget that. What sort of colouring could work? So how, in fact, maybe instead of thinking what sort of colouring could work, I'm going to try to think what property would the colouring have to have that would enable me to prove anything. So, for example, do I want to say that that the number of colours that I cover with each square is sort of balanced in some kind of way? That means that I can't have just end up with one thing of one colour and nothing of any of the other colours. I could do that if I could somehow prove that the difference between the number of things covered of certain colours was even, or a multiple of 3 perhaps. But I'm having slight trouble with that, because if, for example, let's just have a little quick look at this. So if I do a normal chessboard colouring, it doesn't seem to, I don't think sort of deciding how many black squares are covered and how many white squares are covered really gets me very far, because if, for example, I take a 3 by 3, then that could cover 5 blacks and 4 whites, but then if I move it 1 to the right, it'll cover 5 whites and 4 blacks. So it seems as though it can sort of undo whatever I did. But I wonder whether if I do that thing that I did before of doing a sort of chessboard, let's just forget all the white squares altogether, and then I'll sort of have I'll colour, let me say, I'll just write 0 here, 1 here, 0 here. So I take, let's say, the black squares of a 5 by 5 chessboard and colour them. If I sort of turn myself diagonally and colour them alternately with 2 different colours that I've just called 0 and 1 as some sort of label, doesn't really matter. I'm just going to think, this was a bit of a guess, but I'm going to think what happens if I put down a 2 by 2 square, a 3 by 3 square, and a 4 by 4 square. So if I put down a 2 by 2 square, I'm going to cover the same number of 1s as 0s, however I do it. If I put down a 3 by 3 square, I'm going to cover 4 0s and a 1, or 4 1s and a 0. And if I put down a 4 by 4 square, it looks as though it's going to be the same number of 0s as 1s. And if I put down a 5 by 5 square, then I have 9 0s and 4 1s. So let's just have a look at my options. So 0s and 1s. My options are either one of each, that's if it's a 2 by 2 square. If it's a 3 by 3 square, it can either be 4 and 1 or 1 and 4. If it's 4 by 4, then it's got to be 4 plus 4. And if it's a 5 by 5, then it's got to be 9 and 4. And by sort of adding and subtracting these things, bearing in mind that the 5 one, I'm only allowed to use once, because if I use it twice, I've sort of undone all the good work that I did by using it once. But I've got two cases I can think of here. If I don't put down the entire square, then I know that the number of noughts and the number of ones are going to differ by 3 mod. Differ by a multiple of 3, because adding a 2 by 2 or a 4 by 4 makes no difference to the number of to the difference, and adding a 3 by 3 changes it either by adding 3 or subtracting 3. And what have I got to start with? I've got 1, 2, 3. So the starting difference is 2 mod 3, because it's 9 take away 4, which is 5, which is 2 mod 3. So if I never put down this 5 thing, I will never be able to get to a difference of 1 mod 3 or 0 mod 3. Is that what I meant to say? So if I want to end up with just a single square, then the difference between the number of noughts covered and the number of ones covered will either be 0 if it's... that doesn't quite work, because I could have the number of zeros minus the number of ones being... So I could, in theory, cover one of these 4 squares here without ever doing the whole thing. So maybe I should just see whether that's possible before I try to prove that it's not possible. So is there some way of ending up covering this square and nothing else? I better give that a try. So I'm going to... That's covered this thing. And then maybe I'll put in this, make it a bit clearer, put in this 3 by 3. So now that's covered. So I'm going to have noughts and ones now, talking about how much things have been covered. So that's been covered 0 times, that's been covered 0 times, and all this lot's been covered once. Sorry, wrong way around. No, it is the right way around. So I put down a 2 by 2 and I put down a 3 by 3. I'm seeing whether I can get it with... I know that I can't use this... I think I can't use this 5. I need to just get my head clear a little bit. So if I do put down the 5, then I've got a difference of 2. My ultimate aim is to end up with a difference of noughts minus ones being still 2. So it's actually, if I don't use the 5, I start with 0, and I want to have the difference being... but then I could have the difference being 0. So this invariant sort of is not seeming to do me all that much good, actually. But I'm going to try the same idea, but instead of with the black squares, do the white squares. I may come back to this. It may not be doing me no good at all, but I think rather than pursue it to the bitter end, I think I'd be in it. I think it would be silly not to just see what happens if I do the same thing, except that this time I go 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0. And in fact, there's no harm in looking at both together, now that I come to think about it. So my colouring in that case would be one that I've already considered. Basically this. So now actually I just going to have a new table. Noughts, ones, twos, threes. So if I put down a 2 by 2, what effect does it have? It adds 1 to all of them. If I put down a 3 by 3, it's going to put 4 ones and a 0, and 2 of the other things. Yeah, so it's going to be 4 of one thing, 1 of one thing, and 2 of the other thing. So it'll be 4, 1, 2, 2, 1, 4, 2, 2, 2, 2, 4, 1, 2, 2, 1, 4. If I put down a 4 by 4, that's going to be something like 2 of everything, 4 of everything, I mean. And if I put down 5 by 5, then I get 9 noughts. I've already done this, so 4 ones. And how many 2s and how many 3s? It'll be 6 2s and 6 3s. So now does that help? So that means that the number of 2s and 3s is going to remain the same. So this was actually extremely helpful. The number of 2s and 3s, the difference between the number of 2s and 3s stays the same, mod 3. If I add 2 lots of things, if I add a 2 by 2, they both increase by 1. If I add a 3 by 3, they both increase by 2, or else one increases by 4 and the other increases by 1. 4 by 4, they both had 4, and 5 by 5, they both had 6. So this, it looks as though now it was overkill potentially to consider the squares that are not coloured in this diagram. So the noughts and ones here correspond to the 2s and 3s over here. So what can I conclude from that? That I certainly can't get a single square if it's any one of these squares here. Because if I did that, then the difference between the number of noughts covered and the number of ones covered would be 1, which is not 0 mod 3, and there's just nothing I can do to change it mod 3. So could it be that given any, if I call these ones the black squares, the ones that are covered by noughts and ones in this diagram, and the ones that are not covered here, could it be that any black square can be done? I know that the center square can be done. Have I been, perhaps I've just not been assiduous enough in trying to do, for example, the corner squares. So let's have a go at a corner square. I should be able to get some clue about how to go about it just from thinking about these. So I'm going to have to use the 5 somehow, because everything else makes no difference mod 3. And it's the number of, I'm concerned with the number of noughts minus the number of ones. I'm back to being slightly confused again. So the starting, if I want the number of noughts minus the number of ones to be 2 mod 3, but I don't. I want the number of noughts. So somehow I managed to get a nought in the middle. Let's just revisit how that was done. It was done here. So to do that, I added the entire 5 by 5, which gave me, what did that contribute to the difference between, to the number of noughts minus the number of ones? It made it up to 5, which is 2 mod 3. And then when I added this, and this, and this, and this, each of those didn't change the difference between the number of noughts and ones. And this one added 3 to it, and this one added 3 to it. So I seem to end up not having changed but I only care about the parity of the number of, what am I saying? Yes, I am a little bit confused here. So what's happened is that this naught has been covered 3 times. Rather than just once. So the number of, so if I count things with multiplicity, help. Then I do get that yes, I've got that thing is covered 3 times, and so all this mod 3 argument doesn't seem to show quite as much as I hoped, because I wasn't allowing for the fact that I could cover something 3 times and then its parity would change, and then something else 0 times its parity wouldn't change. So I can't really, it's mixing a parity in mod 3 is a little bit of a dangerous thing to do. So is it actually even correct that I can't so what if I just do consider how many times I cover things mod 3? But why should I care about the number of times I cover things mod 3? I only care about the number of times I cover things mod 2. So maybe this whole colouring is not so useful. But can I find a colouring such that some difference is always going to be even for a certain class of things that gets coloured? So if I want the difference between the number of noughts covered and the number of ones covered, for example, always to be even, then because there's quite a lot of pressure to write this down. When I cover just with a 2 by 2, then this seems like an extremely natural thing to write down. But then when it comes to 3 by 3, I've got a difference that's odd. So could I have done anything different? Well, let me just have a little, that did seem to be a little possibility there. So I'm going to try to write down something that whenever you cover it with a 2 by 2, the difference is even, and whenever you cover it with a 3 by 3, the difference is even as well. So I'll put a naught there. And instead of putting a 1 here, I'm going to put a 1 here just for the hell of it. So that deals with that 2 by 2 square and that 2 by 2 square. And so I think it'll look sort of nice if I do that 2 by 2 square and that 2 by 2 square. Now I want to do something slightly different, just for the sake of being different. So, or maybe I could just carry on like this. Would that work? What if I just do that? I'll try something simple first of all, rather than trying to be over clever. Whoops. 0, 1, 0. So if I cover with a 3 by 3, that doesn't work. Because I could cover with that 3 by 3. So I did need to be different. So let me put a 0 here. So that 2 by 2 now covers 0, covers things equally. So I'm going to put a 0 here and a 0 here. And now I'll just be symmetrical. Does that work? So if I put a 3 by 3 down here, that covers 3 and 1. Put a 3 by 3 here, it's 2 and 2. 3 by here is 3 and 1, 3 and 1, 2 and 2, 3 and 1, and 4 and 1. So that one didn't work, but maybe I don't mind so much about the center square. So far I've got a colouring where the only thing that can go wrong is if I use this 3 by 3, in which case it covers 4 of these and just 1 of these. And the difference changes by 3, but I'm sort of not trying to prove that I can't cover the centre square, so I have a sort of hunch that that doesn't necessarily matter. So let's just pursue this line of thought. So if every 2 by 2 covers the same number of noughts and ones, then trivially every 4 by 4 also covers the same number of noughts and ones, because you can decompose it into 2 by 2s. What about the whole 5 by 5? We've got 2, 3, 4, 5, 6, 7, and 4. So this 5 by 5 doesn't work, but again, we could argue that the only reason it doesn't work is we've got this middle one. So I'm not quite sure exactly what I'm trying to say here, but I think I'd like to argue now that if I try to cover any of these squares exactly once, apart from the middle one, I'm going to be in some difficulty. So maybe I'll try and argue about that square there. So if I colour this square and cover this square an even number of times, then each time I cover this 0, I'm going to be using either a 2 by 2, which will cover a 1, or it'll cover exactly 1, or I'll cover a 3 by 3, in which case I'll be colouring 3 zeros and a 1, or a 4 by 4, in which case I'm going to be covering 4 zeros and 4 ones, or a 5 by 5, in which case I'll cover yeah, so it depends. If I use the 5 by 5, then I cover this central square here. And if I don't, what is this telling me? This is such a weird colouring that it sort of feels as though it sort of morally shouldn't be terribly useful. I suppose what I do learn from it is that if I'm going to cover, if I'm going to end up with this covered an odd number of times and all other squares covered an even number of times, then the total number of these things that I cover has to be odd, and the only ones that cover it an odd number of times are this central thing. To cover an odd number of them is this central thing and the entire square. And so I'm going to have to use either the entire square exactly once and not this middle 3 by 3, or I'm going to use this middle 3 by 3 exactly once and not the entire square. And then it's hard to know exactly what to say after that. This is taking me a much longer time than I was expecting. So I think what I'm going to do is I'm going to switch tack a little bit. I think I may have got myself very close to a solution and just not noticed it. So if you're watching this and tearing your hair out, wishing I'd said something, then you have my full sympathy. But what I'm going to do is write down some, I think this is something I should have done earlier. I'm just going to make a note of some things that I can generate. So for example, out of two 2 by 2s next to each other, that's not so nice. I get something that looks like this. I can get two sort of not completely adjacent. Well, from one 2 by 2 I can get two adjacent ones. If I add two of them I get two that are like this, and if I add three of them together I can get, I can sort of shift it over a bit more and so on. So I suppose I can always get, that allows me also by the similar argument, if I shift this thing, which I can do, I can get any rectangle like this, so the four corners of a rectangle. So how do I do it? I sort of just take a 2 by 2, move it along, and then I end up with one by 2 here and a 1 by 2 here, and I can shift that downwards by the same sort of approach and add and keep doing that, and I get a kind of telescoping sum, and I just get left with the four corners. So if I can do that, can I use that to get other interesting stuff? So if I only ever add 2 by 2s, then I'm only ever going to get an even number of squares at the end. So I also consider a 3 by 3, and I know that I can get the four corners of it. So I could also, if I wanted to, get a sort of inner cross like that by adding a 3 by 3 together to its four corners, and what I'm left over with is the inner cross, mod 2. If I add, say, this 2 by 2 square, then I'm left with that square, and that's not very well drawn. That square, and that's still not very well drawn. That square, and that square. So 1, 2, 3, I can get that sort of picture. Which is not necessarily super helpful still. if I add a, I don't know, add a 3 by 3 to a 3 by 3, what happens if I add 4 3 by 3s together in this sort of way? I don't think it's going to be all that nice, but then I'm going to get this, 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 and this. And then by the rectangle lemma, so to speak, I can cancel out all this stuff and just end up with the central square. But I knew I could get that central square anyway. But that looks potentially a little bit interesting. So what if I take a 3 by 3 and add like that? So I add things a bit more closely. So now I've got those 4 and this central 2 by 2, which looks supremely uninteresting because I knew I could get those 4 and the 2 by 2 from the rectangle lemma again. So what is stopping me doing something similar to this, but not putting them in the middle like that? So what I'm trying to say is I have a 3 by 3, and instead of intersecting it with a 3 by 3 or adding a 3 by 3 like that, I want instead to add one where it is this, and can I get this shape here? So that's my new question, and I think I can't necessarily because the rectangle lemma doesn't help me do it. Because I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 squares, so I would need to get it out, make it out of 3 by 3s. And this actually feels like an important consideration. Actually, because 3 by 3s seem to be so play an important role here, I just wonder, going back to colorings, whether I get anywhere if I just do a mod 3 addition table type coloring. I really don't know what this is likely to give me, but it seems worth trying. So what can I say if I put down a 2 by 2, it's going to cover 2 of one and 1 each of the other 2. It's hard to know why that would be of any use, but there we are. If I put down a 3 by 3, it's obviously going to cover the same number of everything. And if I put down a 4 by 4, it's going to be 6 of one, 5 of another, 5 and 5 of another. That's what it looks like. Yeah, that's what it'll be. So I get 6, 5, 5, that's for a 4. For a 3 it's 3, 3, 3. And for 2 it's 2, 1, 1. And for all 5 it's 1 plus 4 plus 3, so that's 8. 2 plus 5 plus 2, which is 9. And 4 plus 3 plus 1 again, which is 8. And the slight difference is that this 898 has to be the number of noughts, the number of ones, and the number of twos, whereas these you can permute them however you like. So I could also have 565, 556, and 112, and so on. So does that get me anything? It doesn't feel very useful. So I'm still back to the question, what actually am I hoping to get out of a colouring? So ultimately what I want to prove is that what I want to do is to see whether I can generate a given point in the square using, or a given function that's 1 in the square and 0 everywhere else, from a certain collection of other squares. And the normal way of doing that, or normal way of showing that you can't, is to find a linear functional mod 2 that takes the value 1 on that square and 0 everywhere else, and that's actually equivalent. So I should really, I don't know why I've been wasting time actually. I should have been thinking along these lines right from the start. I really have to find, if I want to prove that something's impossible, I have to find a function, a 0, 1 function, or a set that, if I want to show that I can't create, say, a corner, I have to find a set of squares that contains that corner, but that intersects each 2 by 2, 3 by 3, or 4 by 4, or 5 by 5 square an even number of times. So that's what I'm going to try to do now. It isn't really a colouring unless you think of it as a two colouring. So my square, I was going to put crosses in there. So I need to cover this 2 by 2 square an even number of times. So perhaps I could put in another. Let's just try going up all the way along the row for a start. So how am I going to cover 3 by 3 squares an even number of times? Well, one thing I could do is this, and then this. So clearly 3 by 3s, well, not clearly, not so clear, but 3 by 3s one checks. It covers each an even number of these rows, and so therefore we'll get 3 plus 3 equals 6. 4 by 4, it covers an even number of columns, and 5 by 5, there's just an even number of these things. So that proves that, okay. So I feel annoyed with myself. I should have spotted this right at the beginning. This is a proof that you can't do any of these squares. And then you could similarly prove by just rotating it that you can't do those two squares or those two squares, and so we're just left with a centre square, which we've seen that you can do. Just how does this proof work? So whenever I put down a 2 by 2 square, a 3 by 3 square, or a 4 by 4 square, or a 5 by 5 square, it's going to cover an even number of crosses. So that means that I'm going to flip an even number of crosses. So however many times I do it, if I start with no crosses at all, what I mean is that in each crossed square I'm going to have a plus 1 or a minus 1. Let's phrase it the way the question phrased it. So if I start with a minus 1 in just one of these crossed squares, then I've got an odd number of minus 1s in the crossed squares, and however I choose a square of things to flip, I will end up flipping an even number of crossed squares, and so I'll always have an odd number of minus 1s, and so I'll never be able to get all 1s. By rotating this so that we have crosses down here and down here, I get the same argument. If I can make these ones cross squares, so I can't do that either. And the final part of the argument. Actually, perhaps I could even just put crosses here right away. Let's just check whether that works. No, that doesn't work. There must be some way of getting it to work, but let's not worry about that. Oh no, sorry, I was talking nonsense. So the only square that we can't rule out is the central square, which we've seen that we can make. So I think I was slightly fooled by this belonging in the colouring problems chapter, because I think if this had been in the first chapter as an invariance problem, I would have just straight away gone for something like this as an invariant. But perhaps there was another proof that had in mind. So I've not got halfway through. I've only managed to do one question. I really must get on with some other things. So I'll stop there.